Welcome to week 2, part 3, in which we're going to take a look at descriptive statistics. So, what is statistics? Well, in general, statistics is the study of data, starting from collecting data in a proper way, analyzing the data in various ways, interpreting the results, presenting the results, in an effort so that someone can draw conclusions or make decisions based on the analysis of the data. Descriptive statistics is a corner of this overall business of statistics. It has to do with quantifying and summarizing and presenting representations about a particular set of quantitative data. Okay? So this is a fairly narrow corner. And it's quite in contrast to inferential statistics, in which we're actually trying to make predictions or make general statements about an entire population. Whoops. Come back. About an entire population. But the population is typically much too large for us to study every member of the population, so we have to do this based on a sample of the data. Okay. So, again, descriptive statistics concentrates on a particular set of data that we have, and inferential statistics is broader and tries to figure out how to make general statements about the population. Okay, so in other words, we want to quantitatively, good heavens, quantitatively describe or summarize the information in our data set, and this breaks down into 3 sort of categories. One is to come up with measures of what's called central tendency. That is, what is a typical value? Well, typical value has multiple interpretations. There's what most people think of as the average value or the mean value. But there's also the median value, the value where half of the data is above that and half is below. And then there's the mode value, the value that is the most common in the sample. We're also interested in measures of dispersion, measures of the spread of the data. And this can include things like the standard deviation or the variance of the data. Less scientifically, I guess, we can also talk about the range of the data. That is, what is the smallest value, what is the largest value, and what is the range of values in between those. Now, these are all just numbers, and tables of numbers are maybe not the best way to communicate an understanding of what's going on. So we also want to produce frequency distributions and graphical representations of this information in order to make it easier for people to make decisions based on the data. Here we have a table of information about students. And of course this is made up, but it's representative of our Heinz master's students. We have some number of students. Each of them has a first name, a last name. Each of them is associated with a particular master's degree program and various other attributes that we haven't bothered to list. They also have some number of years of coding experience and an age. Now, in this information, some of the information is qualitative. That is, the first name, last name, the program that the student belongs to. These are not numerical, they're just categorical, okay? Qualitative is often just an alternative name for categorical data, and we can't do things like computing an average first name or an average last name. I suppose we could discover the most common first name or the least common first name or whatever. Some of the data are quantitative, and we can actually do numerical related computations. Specifically, first name, last name, and the program that the student is, as I said, are not numerical. These are categorical. And the amount of coding experience and the age, these are numerical data. In quantitative data, there are also two different subcategories. There are discrete values, 1, 2, 3, 4, 5, what have you, and there are continuous variables or continuous values, which take up an infinite sequence of possible values. All right, so here are some comparisons of diagrams of discrete data versus continuous data. Here we have the number of tickets sold. If the cost is a certain amount, tickets are not infinitely divisible. We have to sell some discrete integer number of tickets. On the other hand, if we're selling grain, let's say, then that is essentially continuous. We're able to compute a cost for any number of fractional pounds of grain, and there are not any gaps or jumps in this function. We have 4 different kinds of variables that we're going to need to deal with in our statistical analyses. The nominal, ordinal, interval, and ratio. Let's differentiate what these are. So nominal just means categorical. Things that are discrete and different from each other, but that don't have any ordering relationship. We might have gender. We don't think of there being an ordering for gender. Eye color. You know, we have people with brown eyes, green eyes, blue eyes, but there's no ordering to those. Dog breeds, of course, there are many different dog breeds, but there's no ordering to those. Here's another example of some nominal data. Ingredients in pizza. We have dough, tomatoes, bell peppers, pepperoni, etc. Arugula. Oh my gosh. All right, I don't want to be invited if arugula is on the pizza, but nevertheless, you know, we don't order tomatoes and pepperoni and mushrooms. They are just either on the pizza or not on the pizza. Ordinal are values that do have some kind of implied order, but there's not a definition of like the distance between these. For example, in the Olympics, medals are awarded, gold, silver, and bronze, and we know that gold is best and silver is next best and bronze is third best, but we don't talk about a gold medal being worth 8 times as much as a silver medal and a silver medal being worth 3 times as much as a bronze medal. There's no measurements applied to these differences. Here we have another example. And in fact, this is a kind of a hint. Topics that you might select for your project. And we just have ordered categories of your preference for these things. So are you interested in doing something involving financial data? Well, strongly dislike, dislike, neutral, like, strongly like. Those are clearly ordered from least like, you know, from the lowest level of like to the highest level of like, but we don't define a specific distance between these things. Then we have interval data where we're able to measure values, and the values come at discrete even-sized intervals. Here we're looking at a Celsius thermometer and a Fahrenheit thermometer. The degrees are 1 unit apart. Of course, the unit for a Celsius thermometer is wider than the unit used by a Fahrenheit thermometer. We could, if we're being extraordinarily picky, talk about, tenth of a degree differences and so on. But for most purposes, we just talk about, degree differences. Like on the weather, they don't tell you that it's in the U.S. anyway. They don't tell you that it's 72.2 degrees out. We just go in discrete intervals: 72, 73, 74, and so on. Here, there's a definite ordering, and the units are known to be the same distance apart from each other. Here we have another interval specification for different categories of humans and the care that ought to be given to them based on some intervals of temperatures. Okay, so if someone comes in to the emergency room and their temperature is 95 degrees or below, then regardless of their age category, they are in hypothermia and they need immediate care. If their temperature is between 95.1 and 96.9, somewhere in that interval, then for adults and children, this might actually be a normal temperature. They probably ought to be observed, but may not need treatment. But for a baby, this is considered low, and the baby should, be given care and so forth. And then we have normal temperatures, fever, high fever. Okay, so again, the intervals here are approximately the same. Finally, we have ratio, or just real number values, and there is some kind of absolute zero in these ratio values that matters typically. For example, the ages of people. We never talk about a child having a negative age, and age is a continuous value that moves at the same pace. So a year is a year, whether you're 1 year old or 80 years old. Sometimes it's not completely clear which one of these categories a particular piece of information belongs to. For example, if you consider radio stations. What are radio stations? Well, radios, you tune into a radio at a certain frequency. So I don't know, are radio stations interval things? Are there even intervals between radio stations? Well, no, not really. I mean, there's no even distribution of radio stations. So even though there are, frequencies associated with these radio stations, like 90.5 and 101.3 or whatever, we wouldn't consider the station located at 101.3 to be somehow greater than the station located at 90.5. So these are really just nominal, just categorical, even though there are numbers associated with the radio station frequencies. Okay, so anytime you get some new data and you want to figure out which of these categories it falls into, here's a series of questions that you can ask. Is there any difference between the values? If there isn't any real difference in importance between the values, then you just have some categorical data. If there is a difference between the values and the values are in some kind of order, then you have some ordinal data. And if there is a consistent unit of measure between the intervals, then that gives you some interval data. And does the measurement include some absolute zero value? Then you have some ratio data. All right, so you need to consider these questions in order to decide which category of data you have, which in turn will determine the kind of analysis that it makes sense to do. So in our example of this data set about students in Heinz master's programs, the coding experience in years and the age in years are ratio values. There is an absolute zero in both of these cases, and each year of difference in age or difference in level of coding experience is, the same unit as another year of difference in coding experience or age. So it does make sense for us to ask questions about, means, medians, modes, etc. for these ratio attributes, but not for these categorical attributes. Now we can count the number of occurrences of the various categories. This probably makes no sense for first names or last names, but it does make sense for master's programs because there's a relatively finite number, and we know what each of these different master's programs is targeted at. So in the case of a categorical data here, where each of the categories is a pretty well-defined thing, we might do something like create a pie chart and then label the pie chart with specifically which category each of these falls into. So based on this pie chart, the PPMDA program and the HCA program are the two largest. In fact, the pie chart is ranking these from largest down to smallest. And the various MISM programs and MSIT combined looks like they only amount to 40% of the master's programs. This is not real data. It's just an illustration of how to use an image to convey some meaning behind the counts of the number of occurrences of each of these categories. All right, now for the ratio category, there are a whole variety of different visualizations that we can use that will, convey some meaning. Here we have a histogram where we've created buckets of various different widths and counted the number of occurrences of people with these different amounts of coding experience. Here's an example of a data set. We don't actually have this data set, so I can't run live demos on this data set. But this data set has to do with the weights of various different ages of chickens, being fed different kinds of diets. Maybe we've got some agricultural researchers here trying to figure out what the best way is of helping these chickens gain weight. All right, so here we've got in this illustration, we have 578 different chickens, and for each chicken we have 4 columns of data. The first column is the weight. This is the body weight in grams of the chicken. Time is the number of days since the birth of the chicken. So here we have a newborn chicken that weighs 42 grams. And here we have a 2-day-old chick obviously, that is 51 grams. Okay, so if these were both 42 grams on day 0, then after a couple of days, this second chicken in the data set has gained 9 grams of weight. This next column, the chick column, simply associates a level to each of the chicks' weights, ranked from lightest to heaviest, but without necessarily a defined interval of weight between the chickens. And then finally, the diet is simply a category 1 through 4 that indicates which diet the chicks are on. Here again, there's no implication that diet 1 is better or worse than diet 2. They're just 4 different diets that might be fed to the chicks. So, what data types do we have here? Well, the weight and the time, each of these do have an absolute 0. Each of these does have a growing scale. I suppose we could have a chick lose weight over time, but clearly the weight column and the time column here are ratio data. A gram is a gram regardless of how much weight the chick starts with on a given day. Likewise, a day is a day. The level of weight is ordinal, but there's no specification here that each level has some kind of equal width. The chicks that are in level 1 are lighter than the chicks that are in level 2, which in turn are lighter than the chicks that are in level 3, and so forth. But it's not specified that the difference in weight is the same for each level. And then finally, the diet is just categorical. Diet number 1 is different from diet number 2, which is different from diet number 3, and so on. All right. So, what can we learn about our data set now that we know the types, the kinds of data that's contained within each of these columns? Well, it's time to apply some descriptive statistics to this data. We can, for the ratio data, we can ask, such as the weight, we can ask what the minimum and maximum and median weight are of all the chickens in the data set. And we get some numbers here. So apparently somewhere in here we have an even lighter chicken than 42 grams. We also have a significantly large chicken, 10 times the minimum weight, which of course makes sense if you consider chickens. The chicks are quite tiny, but the adult bird is many times larger than the chick. And the median weight is simply at the mark where half of the chickens are of a lower weight and half of the chickens are of a greater weight. We could not compute these kinds of descriptive statistics for the level of weight or for which diet the chicken is on. We can also compute the mean weight of the chickens. Just add up all the weights, divide by the number of chickens, and we can compute the variance and standard deviation of these weights. Okay, we can do the same thing, min, max, median, mean, variance and standard deviation for the age of the chicken in days, but not for the levels or the different categories of diet. We can compute quantiles. Here we've got 4 different quantile categories. So the lowest, we've already described that the minimum weight is 35, so that's the weight at the beginning of the 0% quartile. And so up to the 25th quartile, the first quarter, we have weights ranging from 35 up to 63. And then from 63 to 103, that's another quarter of the chickens. The third quarter of the chickens is from 103 to 163.75. And then the final quarter goes from 163.75 up to 373. Okay, so those are the boundary weights between the lowest weight quarter, the next quarter, and the third and fourth quarters. Here we have a similar kind of summary, but this includes the mean weight as part of the result. So basically, these are the beginnings and endings of the quartiles with the mean value shown in. We see that the mean value is in this third quartile between the median, the 50% value, and the beginning of the final quartile. And here we have a table that summarizes this information for all 4 of the different variables. Well, that provides summary data for all of the variables. We have the description of the quartiles and the median and mean for the weight characteristic and for the time characteristic. Then for the level of the chicken, we just have a count of the number of occurrences of each level. So apparently there are 6 levels that the chickens are divided into in terms of weight. And then we have a count of the number of chickens that are being given each of the diets. Now, here we're told that 506 of the chickens are not categorized into one of these levels. So that may imply some missing data, or it may imply something else going on. Fine. So we've got a whole bunch of numbers here. And a knowledgeable and patient user of this data may be okay with wading through these numbers and trying to make sense of them. But a visual, whoops, that's not what I wanted to highlight. A visual representation of these quantiles would certainly be better than just giving the numbers. And so let's have a look at some better graphical representations of this information. The box plot is a very clean and very easy to understand representation of any ratio data. The box in the middle here is what's called the interquartile range. It shows from the it shows the middle half of all of the data values. From the lowest value in that middle half, in other words, this is where the first quartile ends, and the second and third quartiles begin. So from the beginning of the second quartile to the end of the third quartile is what the box represents. Now, within the box, there's also a horizontal line representing the median value. So half of all values in our data, in this particular ratio attribute, half of all the data are below this median, and half of all the data are above the median. Okay, and this box here is called the interquartile range. Now, below the interquartile range, we have 1/4 of the data, and above the interquartile range, we have the other quarter of the data. So all of the data, all 100% of the data, are represented in graphical fashion here. Okay, now these whisker bars below and above the interquartile range are, so the interquartile range has a certain range. It has a minimum value and a maximum value, and we assume, because it's generally true, that the data tend to be more clumped around the median than they are around the tails. So the rule for creating these whisker bars is that we take 1.5 times the interquartile range above 1.5 times that range above the upper quartile, and the value that we get there is what's called the fence. Then the whisker itself is created where there is actual data. So the level of the whisker, pardon me. Come on now. All right, so the position of the whisker is not necessarily right at the fence. That is 1.5 interquartile range distances above the high end of the interquartile range, because the whisker is pulled back to where an actual data value occurs. Now, if there are remaining data that are even beyond that whisker value, those are just indicated as dots or circles above that whisker. And any dots or circles that we see above that whisker are referred to as outliers that are unexpectedly far from the median. All right. The same thing applies on the lower quartile. Once again, we have our fence, a distance of 1.5 times the interquartile range, lower than the beginning of the interquartile, lower than the low edge of the interquartile range. And from the fence, we pull upward to the next actual data point that exists. And that's where we draw this whisker. Here, apparently, there are no outliers. There are no values that are unexpectedly lower than this whisker that's shown. So this gives you a really quick overview of how concentrated the data are, how spread out the tails are. That is, if we have a short, narrow box, that means that the data are pretty concentrated. And then if we have whiskers with a lot of outliers on either end, that means that there are a number of stragglers that are far away from the central area, and so on. This, of course, is something that you should have encountered in previous statistical training. If not, you'll definitely want to look up what a box plot is and become acquainted with how a box plot is created and what all this terminology means. So we can create a box plot for any ratio data. So in our case, we could create a box plot for the weights of the chicks and for the ages of the chicks, but not for the levels and not for the diet, because those are not ordered. Well, the level of weight of the chicks is ordered, but it's not a ratio, and the diet is merely a category. Alrighty. Another way of representing the ratio-valued information is to show a histogram. Here we've got the weight divided into equal widths. We've chosen to put our labels at every 100 grams of weight. Obviously, a chick cannot have a negative weight, so we've got our absolute zero here on the left edge. And it's clear that this histogram is divided up into buckets that are 50 grams wide. All right, so the number of chickens that have a weight between 0 grams and 50 grams is apparently about 80 or so, I would guess, based on this frequency count here. And then we have the number of chickens that have a weight between 50 and 100. That looks like about 195 maybe. Then between 100 and 150 grams, maybe 120, and so forth. 150 and 200 grams, 200 and 250, 250 and 300, etc. Okay. Now, this is for all of the chicks, regardless of which feed they were being given. We probably want to know, separated out by each different diet, what distribution we have of the, or what distribution, a histogram is a visual representation of a distribution. So we might be interested in having a histogram of the frequency for each one of the 4 categories of diet. So for diet 1 and just for the first year, we have the counts of the number of chicks at different weight intervals. Here our buckets are narrower. Each bucket is 20 wide. So over here on the left we've got from 20 to 40. 10 wide. So we've got 30 to 40, 40 to 50, 50 to 60, etc. And the bucket width is going to depend on, we can choose the bucket width independently for each of these different histograms, depending on how many chicks there actually are. So here in this second plot, there are actually many fewer chicks being represented than in this first plot, because notice in the first plot, our frequency scale is going from 0 up to 35. Looks like there are about 34 chicks in this 40 to 50 gram bucket. But over here, although the buckets are wider, the number of chicks in each bucket is fewer. Okay, and then similarly for diet 3 and diet 4. Can we tell from glancing at this which diet is better? It's not clear to me that we can, but it's interesting information. One problem that we have is that the upper end of these scales differs. So for diet number 1, our maximum weight bucket ends at 140. Here, our maximum weight bucket goes out to, let's see, 150. It looks like maybe it goes out to 180 or something like that. If we wanted to have a better visual comparison between these, then we really should have arranged for the bucket widths and for the ranges to be the same in all of the plots. Here is the same kind of plots, but after the first year. Okay. All right, so as a review, we've got 4 different types of variables to analyze. Nominal or categorical, ordinal, which are ordered but not necessarily at equal-sized intervals to each other. Then we do have interval data, where the intervals are of equal size. And finally, ratio data, where we have an absolute 0 and numerical values ranging from the minimum up to some maximum. So what kinds of analysis can we do with these? Well, with nominal data, as a reminder, that would be something like pizza toppings that either exist or don't exist on a particular pizza, and we can count the number of occurrences of each of these nominal items, and from the counts we can compute percentages. We can also identify modes. That is, maybe you've asked for triple tomatoes, triple level of tomato on your pizza. So tomato might be the most common ingredient that you've added to your particular pizza. For ordinal data, we have ordered values, but not necessarily an equal width between the various values. And here we can do a little bit more than we can with just plain nominal categorical values. We can still do frequencies and counts, percentages, modes. We can also compute a median value. We can specify, which of these levels, is in the middle in terms of the number of responses. We can also specify the range. Maybe in our particular data set, 0 people selected strongly dislike, and so the minimum value here might be dislike, and the maximum value might be strongly dislike, and we can rank based on the number of people, the number of responses that we got for each of the categories. We can determine which of the categories was the most commonly selected, and the next most commonly selected, and so forth. For intervals, we can do even more. Here we have GRE exam percentiles for the verbal part of the GRE and the quantitative part of the GRE. To be in the upper 90% on the verbal exam, you need to score between 162 and 170, whereas for the quantitative exam, you have to score between 166 and 170, and so forth. We can do everything we could do with ordinal, frequencies and counts, percentages, mode, median, ranges, rankings. We also can compute means and variances and therefore standard deviations. We can do t-tests. We can do analysis of variance. And we can do correlations. We can compute correlations between different interval attributes. And then finally, for the ratio data, such as the age of people, maybe in addition to the age of people, we've got the weight of people or what have you. And once again, we can compute the same kinds of statistics to try to gain an understanding of this information. All right, so let me do a little demo here to show how you go about performing some of these kinds of calculations using pandas in Python, and also how you can create some different kinds of plots. All right, so I'm going to pull up my Python shell here. We're going to start out by importing these modules that are essentially always used for any kind of data analysis. We've got NumPy, pandas, which makes use of NumPy, and then the matplotlib.pyplot module that has a lot of plotting facilities in it. Now, we're just using made-up data to illustrate the statistical computations that you can do here. And the made-up data is a collection of random integer values. Okay, now in order for you to get the same values that I'm getting, I am setting the seed for the random number generation within NumPy to 0. If you set the seed to something different, or if you just don't use a seed, then you'll get different values from what I'm getting here. The randint function within NP's random submodule allows me to specify the beginning value and one past the final value for the range of values that I want to generate data from. So by saying 0, 101, that means I'm asking for values between 0 and 100 inclusive. The number of values that I'm asking for here is 20. And this will generate an ND array. I'm using the variable A20 to refer to that ND array of 20 random integer values. And then I'm simply printing those out. So let's give this a try. I've already got my 3 imports done. So let me set the seed. np.random.seed is set to 0. And then I will get my random array. A20 is np.random.randint. Okay, and we see that we can specify the low value, the high value. Now that's actually one past the the top value that will be generated, and then the size. The data type that we're going to get for this is integers. Actually, technically, on my Windows machine, these will be int32s. If you're doing this on a Mac, you'll get int64s. All right, so I'm going to go from 0 up to but not including 101, and I'm going to ask for 20 values. And here we are. The len of A20 is 20. If I just display A20, there's my array. Or to display things a little more cleanly, I can do what's done here on this slide. Print values. I'm going to have the end of this output be one space rather than a new line, because I want values to appear followed by each one of my random values. Whoops. That didn't quite work the way I wanted. Okay, the reason that didn't work the way I wanted is because of my shell. Even though the print function did not generate a new line character, my shell did generate a new line character so that it could show me another prompt. But in any case, now I'm going to loop through for each value in the array A20. I'm going to print that value and then a space. So each of the values is going to be displayed on the same line with just spaces in between. Now, if we visually scan through this data, we can notice that we get 67 a couple of times. We get 88 3 times. We're not getting any really low values. In fact, I only see 1 in here. 9 is the only single-digit value that we've got. And we're not getting any values up in the 90 either. Okay, so, random data has whatever characteristics it has. So that's that part. Now let's actually do some analysis and some plotting. In order to conveniently do statistical analyses and plotting, I do want to put my data into a data frame because the data frame has many statistical capabilities built in from Pandas, and it also interacts very conveniently with plotting facilities. So let me first create this data frame. So I'm going to just call my data frame df, and it is a pandas data frame in which the data are these values in this ND array A20. I'm only going to have a single column of data, so this is not going to be terribly exciting. We're not going to be able to do things like correlations between different columns of data. But let me specify that the list of column names is just value. And I'm going to accept the default labels of 0 through 19. Okay, so I've created my data frame, and here is my data frame. I've got a total of 20 values from 0 through 19, and there are the values. Now, in order to compute the mean, the Pandas data frame has a mean function directly defined, which will give me back the mean on a column-by-column basis. Since my data frame only has one column, I'm only going to get a mean for that one column. And in addition to being able to compute the mean, the data frame statistical logic also includes a median function as well as a mode function. So let's see what these things are up to. Now, in order to fit things neatly onto this one slide, I have used a part of the Python language that you may have forgotten. You are allowed to put multiple Python statements into a single physical line by typing a semicolon to separate each of the statements from each other on that physical line. So I'm going to display a line containing the word mean, and then I'm going to display the mean that I get from this data frame. Okay, so I will print the word mean, and then I will compute the mean of all the columns in the data frame. And of course, in this case, there is only one column. All right, so there we go. So the mean of all the mean value for each of the columns in this data frame is, well, for the column named value, it's 58.3. So we just add all the values up, divide by 20, and that gives us 58.3. We can do the same thing for the median. I'll just copy and paste and change mean to median. All right, so that tells me that half of the values are less than 64.5 and half of the values are greater than 64.5. Now, because there are an even number of values here, the median is the average of the middle two values. Let's have a look at this. If I'll just use A20 since it's got the same numbers in it. Let me throw A20 into a list. All right, so M is a list constructed from A20. And I threw it into a list because I can just do an in-place sort. And now, because the length is 20, whoops, the len of M is 20. Okay, so that means the subscripts go from 0 to 19. And so the middle two values are going to be at M sub 8 and M sub 9. My mistake. Okay, no, my mistake. Okay, so 0 through 9 are the first 10, and 10 through 19 are the second 10. So I messed up. I should have asked for M sub 9 and M sub 10. And what we see here is that if we take these two values, 64 plus 65, and divide by 2, that gives us the 64.5 that was computed as the median. If we had an odd number of values, then we would simply choose the middle value after sorting, and that would be our median for an odd number of values. Okay, now the mode is the most common value. This may or may not be of any use to know for this particular data set, but we can do it. Let me copy and paste this median stuff down. And instead of median, now we're going to get mode. Well, we had previously noticed that there were a couple of 67s a couple of 87s and 3 88s in this random data. So we're told that the mode for this particular column is 88. All right. Now, the data frame also has a table of descriptive statistics. And let's see what we get from that. This is going to give us the minimum and maximum and the quartiles, as well as the mean, I believe. Let's check it out. So we've got the descriptive statistics, which is df.describe. Cool. All right. So there we go. So we got the count of the total number of values. We got the mean and the standard deviation of the values, and then we have the minimum and the maximum and the boundaries of the quartiles. All right, which was, the same kind of information that we saw in the descriptive statistics about the chicks in our feeding experiment. Well, so this table of numbers may or may not be easy to contemplate. Let's try to do some graphics. I had mentioned that box plots are very helpful for giving a detailed description and summary of what's going on with ratio data. So let's do a box plot. We're going to create a box plot for each of the columns, but of course there is only one column. df.boxplot. And because I'm using idle, I also need to throw in this plt.show thing, but you won't have to do that in Jupyter Notebooks. Okay, and so here we are. Here is my box plot. I can just change the size of this so that it's easier to see what's going on with the box plot. And there are a lot of other parameters that I could use for the box plot function to change the background and things of that kind. The lines used for this box plot are kind of thin, so I can do things like changing how all of that stuff appears. But what I observe here is that half of all of the values in this random sample that I got fall in the range from about 83 down to about 42, it looks like. Okay, so from 42 up to 83 accounts for half of the data. Does that make sense? Let's, I can't access idle again until I close the graph, which I don't want to do. Okay, so half of all the data falls between about 42 and 83. Then the values in the lower quartile fall between this whisker at 9 and about 42. And the upper quartile all fall in this range from about 84 up to, well, we know it's 88, okay? So the breadth of values for the lower quartile is much wider than the breadth of values for the upper quartile in this particular sample of some random integers. Now, if we generated a much larger sample, assuming that this sample is being drawn from a uniform distribution of integers, we would expect this box plot to converge over time to where half of the values were falling between 25 and 75, and 1/4 were above 75 and 1/4 were below 75. Okay, so that's the box plot. And we can also do a histogram. Let's have a look at a histogram. So here we say df.plot, and one of the kinds of plots we can ask for is a histogram. df.plot, where kind is hist, and plt.show. And here we are. Okay, so we can see from the histogram that there is quite a lopsided number of values that fall between 80 and 88. Okay, with fewer numbers down lower, and of course there are gaps in here as well. All right, so now I'm dying of curiosity. Let me generate a much larger anti-array of random values. Let me create df2 to be a pandas data frame in which my data are going to be from nd.random.rand_int. My low value is going to be 0. My high value is going to be 101. That's one beyond the highest value. And this time, let's have the size be 200,000. And for the column names, I'm only going to have one column, and that is, as before, going to be value. Now, let's have a look at the box plot for this much, much larger sample. Oh, I was very confused while I was seeing a box plot that looked like my previous one. Well, it's because it's because I did create a box plot from my previous data, so that wasn't very bright. We want to say df2.boxplot. df2.boxplot. And excellent. This is what I would have expected. The middle half is in a range from about 25 up to about 75. The median is right about at 50. And the entire range of values goes from 0 up to 100. So again, all of the data are represented within this box plot. Alrighty, so that gets us to the conclusion of this introduction to doing descriptive statistics.